146 evaluation data. The below chart is the class of action that we actually choose. Next, I'll talk about the flowchart of proposed model. Label data and unlabeled data will have different process. For label data, it will be width transformed first and become the input of spatial temporal graph convolutional network. The output prediction will be calculated label data loss with ground truth label. On the other way, there's two different operations for unlabeled data. It will have weak transformation and strong transformation respectively. Notice that the two unlabeled data input is the same data. For the model output of weak transformation side, it will first multiply by the mask filter and become as pseudo label. Meanwhile, the strong transformated data will also obtain a prediction by the spatial temporal graph convolutional network. We can acquire the unlabeled data loss by strong prediction and pseudo label. For prediction of the weak transform, we can obtain a class with the greatest probability. If the probability is greater than the threshold, the mask filter will set to 1, otherwise it is 0. We call the weak predictions which have 1 for the mask filter as pseudo labels. There's a concern for the early training process is that the max probability for pseudo labels are not big enough to pass the threshold. So we use adaptive threshold as a solution. The threshold can be changed during training while the model learns more information for unlabeled data. The threshold will gradually set to initial state. And there's the related formula for adaptive threshold. You can see that class accumulation is the count of the specific class pseudo label, and it is divided by the max of the all class pseudo label. And the class threshold is calculated by the threshold and multiply the class accumulation for the pseudo labels class, and divided by 2 minus the class accumulation. The spatial temporal graph convolutional network has the structure as the below. First, the data is normalized by batch normalized layer, then sent into STGCM block. After that, we use pooling layer and full connection layer for classify the output. The STGCM block works as below. The input is first sent to GCM block and residual TCM block. The GCM block is sent to the TCM block next. Finally, we sum the residual outcome and TCM block outcome and gets the output via redo function. Next, let's talk about graph transformation. The weak and strong transform are composed with graph transformation. We use feature masking as our transform strategy. We randomly pick up joint and replace the joint data with specific value. You can see that the white point seems like the joint we randomly pick up to replace value. In our research, we experiment 5 kinds of graph transformation to choose the better one. For trans type 1 to type 3, we replace the x, y situation and score data with particular value. For trans 4 and 5, we only replace the score value. Notice that in trans 5, we don't choose joint to mask for weak transformation. Before talking about the experiment results, There are some indicators needed to explain first. For unlabeled training, we use impurity as an evaluating indicator. Impurity is the count of pseudo labels which are not equal to ground truth labels divided by the total amount of pseudo labels. Next, the mass rate is the total amount of pseudo labels divided by total amount of weak transform predictions. The final loss that is used to backward the model is label data loss plus unlabeled data loss. Let's talk about our experiment. First, we compare for different classification dimensions. What is the different classification dimensions? You can see the described below. First, we have for clip output, we generate the probability for 10 cases for each one clip. But for the joint output, we generate the output for 17 joints and each joint for 10 cases. So you can see the shape below. And also you can see that for our experience, the clip output and let's use this adaptive threshold and trans type 5 get the better accuracy. Next, we experiment on graph transform. There's 5 methods of graph transform we talked about before. And we have made some experiments on these 5 methods. And you can see that for method transform 5, it's got the better accuracy. Next is the different threshold and whether we use adaptive threshold gets a better performance. And you can see that we use threshold at 0.98 for adaptive threshold get the better accuracy. And also we have double the training epochs to research then whether the model can learn better. And we find out that the clip output, let's use adaptive threshold 0.97 and use transform 5 get better performance. And that is the comprehensive comparison. On the top is the baseline we want to go through, and it's got 77.50 accuracy. And the bottom is our best model. Let's use clip output and adaptive threshold 0.97 and use transform type 5. For conclusion, by cooperating STGCN and semi-supervised learning strategy, the proposed architecture requires 79.83 accuracy compared with supervised learning as 77.5. While graph transformation is important in this search, we have to notice whether the transformation strategies may distort the data or not. For future work, I have listed 3 kinds. First, complements experiment data. And second, visualize the relationship between the prediction and adjacency metrics. And next, search for better graph transformation method. And here is my reference. And thank you for your attention.
Okay, thanks for the introduction about your proposed method. And I have one question for you to ask. Okay. And finally, to each experimental result, you have shown that the method of the graph transformation will greatly affect the performance for the classification. So can you give us a conclusion about what point we should consider about choosing the graph transformation for future work?
I think the other transformation methods need to be not to change the XY situation for the joint point. For better action distinguishable, or we can try to replace the XY information by the local joints instead of the global joint, because I replaced the joint with like average or standard deviation. I use the whole joint to calculate. I think we can use maybe the local or nearest joint to do it.
Okay, thanks.
Okay, my question is, what is the disadvantage of the semi-supervised learning?
First, it takes much more time for training. Like we talk about the double training epochs, it takes about 12 to 13 hours for training. And for normal training, it takes about six hours. But for supervised learning, we maybe just use 1 to 2 hours for the whole training process. And also, you have to make sure that the unlabeled data distribution may slant the model attribution.
Is there any question on the floor? Okay, if no question, we invite the next speaker.
Okay. Hello everyone, my name is Pen Xu, and my advisor is Chen Hongli. Today, I'm going to talk about my research, which is collision avoidance for AGV navigation using a time-elastic path algorithm. And this is the outline. First, I will introduce what is AGV and why dynamic avoidance is necessary. And next, I will talk about COSMAP and TED algorithm. They play an important role in dynamic avoidance. Then I will introduce the simulation tool I use, including agent, world, and demonstration. After the simulation part, I will introduce the real AGV test, including hardware configuration and software architecture. Finally, I will show the demonstration and talk about the conclusion and future work. So what is AGV? AGV is a mobile robot that follows a predefined path or a set of instructions to perform various material handling tasks without human intervention. Because it is flexible, accurate, safe, and productive, it can do things such as automotive, manufacturing, logistics, and healthcare. And dynamic environments are those that are constantly changing, such as manufacturing or warehouse facilities, where there are people, other vehicles, and obstacles that can move unpredictably. AGV needs dynamic avoidance function to ensure safe and efficient navigation in dynamic environments, prevent collisions, increase efficiency, and reduce the need for human intervention. And this is COSMAP. COSMAP is a Greek-based representation of the environment around a robot, where each cell in the grid is assigned a cost that reflects the level of difficulty or danger associated with traversing the cell. COSMAP has 3 layers, which are static layer, obstacles layer, and information layer. The static layer is composed of the map produced by the slant stage. The obstacle layer is composed of the current environmental information received by the sensors on AGV. The inflation layer increases the cost of cells near obstacles or other areas that should be avoided, creating a buffer zone around them. The cells in the buffer zone are assigned higher cost, making it less likely for the robot to plan the path through them. And in this page, we can see how COSMAP works. Green points are initial and goal. The green line is a global plan, which is generated by a global planner. Global planner generates paths only with a static map. And the red line is the local path, which is generated by the local planner and dynamic avoidance algorithm. The local planner generates the path with all layers of COSMAP, so the information of the dynamic environment is included. Next, the black area is the obstacle, and the yellow area is the inflation area. In this COSMAP, we can see the local planner generates a new path to avoid collision from the original path, which is generated by the global planner. And the new path avoids the inflation area and creates a buffer zone. And next, I will introduce the TEB algorithm. This method treats the two-dimensional path as a rubber band, which connects the starting point and end point, and allows the rubber band to be deformed. The condition for deformation is to treat all constraints as the force of the rubber band. Everything that might cause collision can be constraints: global path, obstacles, robot velocity, and more. And its advantages are real-time planning, smooth trajectories, and elapsed time optimization. This is the control flow of time elastic band. It has initialized phase, path plan phase, and motion control phase. In the initialization phase, an initial path is enhanced to an initial trajectory by adding default timing information respecting the dynamic and kinematic constraints. In the path planning phase, it generates TEB states by path, obstacles, and the state of the robot. All TEB states can be transformed into a hypergraph and be optimized by VIDEO framework, which is a popular open source framework for optimizing nonlinear least square problems. After verifying the optimized TEB, the path will be adjusted. Then control variables V and omega can be calculated in the motion control phase to directly command the robot drive system. Before every new iteration, the reinitialization phase checks new and changing waypoints, which can be useful if waypoints are received after analyzing later scan data. In this part, I use the raw stage to simulate the effect of TEB on AGV. Raw stage is a popular simulation tool used in robotics research and development. Compared to other simulation tools, raw stage offers several benefits that make it a better choice in certain situations. It is easy to use, highly customizable, and use low computational resources. To set up the simulation, first we need to define the agent. The agent's footprint is a rectangle width, which is 0.6 by 0.25 meters. The driving model of the agent is set to differential model. The agent has two ranger sensors. One is at the right front and another is at the left back. Each sensor has 0.05 to 10 meters and 270 degrees of observation area, which has 540 samples. After the agent is defined, I choose a map which is generated by SLAM in the real world. This page will show how TEB works. The left part is raw stage, and the right part is RVs. When the goal is set, the AGV starts the test. The green path, which is the global path, leads AGV to the obstacle and might cause collision. And the red path, which is generated by a TEV algorithm, that AGV be able to avoid obstacles. After avoidance, AGV is safe and is able to reach the goal. Now we know that the TEV algorithm works in the simulation, that it is time for the real-world experiment. The size of AGV is 0.6 by 0.25 meters. It has 4 DC motors and each motor has a steering wheel, which makes the AGV has 2 driving models, Omni model and differential model. In this case, I choose differential model. It also has 2 laser range sensors. One is at the right front and another is at the left back. Each sensor has 0.05 to 25 meters and 270 degrees of the observation area, which has 540 samples. For the software architecture, the AGV is developed based on a ROS system, which enables modular management of vehicle functions. MCLO is a probabilistic localization system for a robot moving in 2D, which uses a particle filter to check the pose of the robot against the known map. Map server reads the map, then publishes map information to the robot. And laser scan reads the scan information, which is current environmental information. RVs makes the robot safe easy to observe. Move base will send the velocity command, which is according to the result of TOSMAP and TEV local planner to base vehicle control modules. And this is the demonstration. The AGV follows the path which will cause collision. After the obstacle appears on the TOSMAP, TEV local planner begins to calculate the avoidance path. And due to the limited computing power, the AGV computer, the size of the TOSMAP is limited to 5.5 by 5.5 meters. So the AGV will stop at the beginning and go backwards to do the avoidance. After the avoidance, AGV is able to continue the test. And through the experiment, we find out localization of MCLO is inaccurate when AGV turns. To fix this issue, I will IMU to adjust the orientation. In the future, further development will focus on addressing blind spots in the laser range sensor, such as integrating visual algorithms to assist in obstacle detection and dynamic avoidance designed for AGV. And this is my reference. And thank you for listening.
Why do you choose differential model instead of Omni model?
Because Omni model is a kind of holonomic models, and holonomic models can cause spinning during the avoidance. And as I mentioned before, the spinning might cause the localization inaccurate. So maybe I will try after I add IMU to the AGV.
Can I have a second question? Which global planner did you use and why?
I use the GISCard algorithm to generate a global path. And I think there is no reason to use the GISCard only, because I think every global planner fits the TEV algorithm as long as the global path can be generated. Okay, thank you.
How about in page 11? While the AGV in the right, if the obstacle doesn't make it stop.
Because the footprint in our face is larger than the robot in the simulation, and it is like a buffer zone surrounding the AGV. So when you see the robot in our face, it's the obstacle, but in the simulation it doesn't. So it avoids the obstacle successfully.
Thank you. Okay, thank you. I think we can invite the next presenter.
Good morning, everyone. My name is Jiazhe Lai, one of the graduate students supervised by Professor Xu. Today, I would like to talk about category level object pose estimation. This is my outline. In the first and second part, I will briefly introduce some background and prior knowledge about pose estimation. Following the third part, I will present a classic paper about pose estimation. Last two parts, I will point out the limitation of this paper and then make conclusions. On this page, I want to answer the question, what is 60 object pose estimation? Object pose estimation refer to the task of determining the 6 degree of freedom pose of an object in 3D space based on RGB images. This involves estimating the position and orientation of an object in a scene. I can honestly say that the goal of the test is to determine the rotation and translation metric. I will explain what is 6 degree of freedom and how to determine rotation and translation metric in the next several pages. The left figure describes the degree of freedom of motion that a rigid object can do. These motions can be represented as a metric. For example, like the roll motion expressed as E matrix, which rotate about the x-axis. The pitch motion rotates about the y-axis, and yaw motion rotates about the z-axis. Then we can further get a general rotation metric by multiplying the BCD matrix. In addition, the remaining motions are expressed as a translation matrix. This page continues the previous page. I will illustrate how robots perceive the world using coordinate transformation. Assume the rotation matrix and translation matrix are known, and a point is in the 3D space, but the position is unknown. If we want to know the position of the point related to the camera coordinate, we can do the matrix calculation as the equation. The right figure visualizes the process of the equation. If we only know the position of the points in the different coordinates, respectively, in a condition, so the equation can obtain the rotation and translation matrix. And next part, I will introduce a classic paper that proposes a method can resolve this problem. Post-estimation tasks can roughly separate two domains: the non-learning approach and learning approach. In a learning approach, instance label and category label are different research subjects that researchers take interest in recent years. I take notes and write to define length. Instance label is defined as the approach which needs an exact 3D CAD model during training and testing time. On the contrary, category label tasks no longer require complete and high fidelity 3D CAD model of object at test time. This page continues with the previous page. I list the advantage and disadvantage of each method. Although the instance label method solves the textual problem, it is still limited to a known object. Therefore, the category label method will focus on an unknown object. In this part, I will introduce the paper as an example of category label post-estimation. The first and second sentence refer to the goals and the main idea of this paper. The third sentence mentions this paper introduced normalized object coordinate space, also called NOCS, a shared canonical representation for all possible object instances within a category. Next page, I will explain NOCS in detail. What is normalized object coordinate space? The normalized object coordinate space is a 3D space contained within a unit cube. Each XYZ position in the NOCS is visualized as an RGB color tuple. According to the first paragraph, we can realize MOCS is just the object of 3D points, but is prepared by color encoding and size normalization. We also can refer to this space as a representation of objects which are all in a given category. We train our network on the perspective projection of the MOCS on the RGB image, the MOCS map. Otherwise, the role of the MOCS map in the network is the ground truth. This paper uses multi-data set for the training model, one of which is synthetic data set called mixed real data. The RGB image is composed of real scene background and synthetic objects. The other data set is real data called real world data, as the picture shows. For a symmetric object, we want the model can afford it. The loss function is designed to assuring the model can steadily predict the MOCS model. The rule of design is an order from top to down. The last rule mentions the loss function of this paper, which is softmax. This page shows the overall architecture of this paper. It is similar to mass RCN in addition to three head networks under the mask head. This paper uses the ResNet FPN network as the backbone for feature extraction and use the FCN network for mask and MOCS map. After we got the mask and MOCS map from the CNN network, we can use mask and depth image with camera intrinsic and extrinsic to obtain points. With the points and the MOCS map, finally do the post-fitting to receive rotation and translation matching. The post-fitting is an algorithm that uses the least squares method to estimate the rotation and translation matching. Because this paper is pioneer of category level post estimation, the others build layer baseline which use MaxRCN for detection and ICP for post estimation compared with the MOCS method on instance level tasks. This paper claims they achieved an MAP of 76.4% for 3D IOU at 50% and at ratio 50%. And MAP 10.2% for the 5 degree and 5 centimeter metric. And MAP 23.1% for the 10-degree 5-centimeter metric. This performance is tested on real-world data. After reading this paper, two limitations are worth discussing: the lack of explicit representation of shape variance limits layer performance. Chain with defined lossless limits layer application to tabletop environment setting. Although I have not made much progress with my research yet, I set myself research direction and planning. For my future work, I will survey broader papers, especially in scene representation subjects, because I think this subject is a more general solution for pose estimation. This paper proposed a novel method for pose estimation. They use the math RCA network to reconstruct the object model, and the pose fitting algorithm is for estimating rotation and translation metric. The result shows the method can achieve good performance. This is my reference. Thanks for your attention.
Any question from the floor? Okay. Sorry, I'm so curious. May I know who your supervisor is? Huh? You mean Professor Shi? So how come I never met you in the CIR lab? Yeah, first time. Huh? Okay. And then I thought for the one who come in front on stage to have to present your own work, right? It is unclear to me. The work presented by you today, it seems taken from the paper, not from your work, right? Okay. So are you year one or year two student? Master year one or year two? Oh, year two. Okay. I think I have to have some discussion with your supervisor. Yeah. Anyway, so thank you for your presentation. Thank you. Do we have another presenter? Or only got four? Four only. Okay, thank you. Yeah. So we thank you for your attention, and then we end this session. See you next week.
心得帮我分年提交哦。
你没有带包包吗？
是啊。
喂，再问一下，李维阳同学在吗？
要按掉吗？要帮你暂停吗？
还在录哎。
学弟，要帮你暂停吗？
VIDEO0035人，就是抓人跟产品抓出来。可是现在知道制作要抓他人，还有是什么惯用脚的，他抓惯用脚的脚尖很酷掉，是那个，然后要分辨每个人都不一样。对，所以你可能就要先判断它到底是右撇子还是左撇子，然后不然你们怎么抓惯用脚？
那这找的一模一样，这找的一模一样，然后结果那医生回答是不一样的，跟我这学超好笑的。过马尾还有录哦，他现在在录。是啥？是啥？啥？是？你让我想象嘛。看不到我朋友报英文报告。好的，没有啊，你知道怎么办吗？每个人都有自己的安排。这地回来了。对啊。
Le lendemain, je te le c'est ça. J'étais seul devant ma paillasse. En vrai, ça. Putain. Sénégalais, genre, il était pas.